Dear all, I am pleased to present our paper titled Efficient Diffusion Training via Min-SNR Weighting Strategy. My collaborators and I are from Southeast University, Microsoft Research Asia, and Shihan Jiaotong University. We will first have a quick review of the basics of diffusion models. Diffusion models are a class of latent variable models to learn the distribution of real-world data. It consists of two processes: forward process to gradually add noise until the signal becomes pure Gaussian noise, reverse process to gradually remove noise to recover the real signal. If we want to generate a sample, we start by sampling a point from Gaussian noise and then gradually remove the noise. The training objective of diffusion model is to optimize the variational bound on negative likelihood. The variational bound can be simplified as this. A loss weight seems a little bit complicated. Optimizing from variational bound can help achieve lower negative likelihood, but the perceptual quality is worse, measured by FID score. In the DDPM paper, the authors reweight the loss function by simply omitting them. A loss becomes simpler and can help achieve better perceptual quality. We can summarize the DDPM training process as training a model to denoise T-noise levels with simple loss weight. Then we want to ask how to balance T-denoising stats. Here T is usually 1000. Is there any better choice than simple constant loss weight? Different tasks have different difficulties. Several methods like RNAVI LG 2.0 and Edify notice that and propose to use mixture of experts for different ranges of time steps. We try to learn something from multitask learning community. Multitask learning tries to minimize a weighted linear combination of per-task losses. In other ways, it means fixing conflicts between different tasks and achieving optimal solution. We also formulate our diffusion training as multitask learning. Multitask learning aims to minimize the norm of weighted gradients from different time steps. The solution is the weight we want. To solve the constrained optimization problem, we add regularization and transform it into an unconstrained optimization problem. We denote the method as UGD. However, optimizing from the objective function has several drawbacks. The first is instability. Limited samples for each time step, gradients are noisy. The second is inefficiency. Calculation of optimal solutions is time-consuming. In order to avoid the inefficiency and instability caused by the iterative optimization in each iteration, one possible attempt is to adopt a stationary loss weight strategy. After exploration, we find Min-SNR gamma loss weight strategy. It is similar to the final loss weight optimized by UGD and is more efficient. Here SNR is signal-to-noise ratio. We make comparisons of the objective values in this equation. Our loss weight could achieve low objective value, close to the solution of UGD. We conduct some experiment to show the effectiveness of our method. Firstly, we compare different loss weighting designs on different predicting targets, such as I0, V, and epsilon. The results are on ImageNet with a VitB backbone. Here are several qualitative results to show the fast convergence. We validate our methods working well on different backbones, VIT and UNIT. We'll also show that our weighting strategy is robust to different gammas. Finally, we make some comparisons with some SOTA methods on Celebamonist 64, ImageNet-64, and ImageNet-256. We find it also works well on EN's denoiser framework. Here are our conclusions. We first analyze the optimization conflicts in diffusion training. Then we present a simple and efficient weighting strategy Min-SNR gamma. Finally, we conduct extensive ablation and achieve SOTA results to demonstrate the efficiency. Thanks a lot for your attention.